Among the countless points of light that adorn the vast, dark canvas of the night sky, one has always captured our gaze and our imagination with a unique intensity. It is not a star, but a world, a steady, wandering beacon with a distinct and ominous reddish glow. This world has served as a mirror for our own hopes and fears for millennia, a silent character in the long story of human curiosity. If you enjoy exploring these grand cosmic narratives, be sure to subscribe to the channel so you are notified of future stories. The world we speak of is, of course, the planet Mars. For most of history, its story was our own invention, a tale populated by gods of war, dying civilizations, and immense canals built by alien hands. But in the modern era of exploration, the story of Mars is finally being told by the planet itself, its secrets whispered to us by the robotic emissaries we have sent across the void. It is a story far stranger, more ancient, and more magnificent than we could have ever conceived. It is a tale of a world that may have once been like our own, a world of water and warmth that lost its oceans and had its atmosphere stripped away into space. To truly know this place, we must journey there, not just through space, but through time, and begin at the very foundation of its identity. Our celestial journey begins as we venture outward from the sun, moving past the inner terrestrial worlds and crossing the orbital path of our own planet. Here, in the fourth position from the star that anchors our solar system, we encounter a world that has haunted the human imagination for millennia. This is Mars, a planet of stark beauty and profound mystery. In the grand hierarchy of our solar system, it holds a peculiar distinction in its physical stature. It is the second smallest of the 8 planets, a diminutive world that is surpassed in its smallness only by the fleet-footed messenger, Mercury, which hugs the inferno of the sun. This rusty globe, hanging in the blackness of space, is a mere shadow of its larger neighbors, a cosmic pebble next to the gas giants that reside in the cold outer depths. Its most striking and famous characteristic, the one that has defined its identity across cultures and epochs, is its breathtaking color. Mars is unequivocally the red planet. This is not a mere trick of the light or a subtle atmospheric tint. It is a fundamental truth of its geology, a world literally rusting away in the vacuum of space. Its surface is saturated with iron oxide, the very same compound that forms when iron is left exposed to the elements on Earth. This pervasive layer of fine, reddish dust covers vast plains and fills deep canyons, lending the entire planet a distinctive and often ominous ochre hue. When sunlight strikes this global layer of rust, it reflects back into space as a deep, ruddy glow, a beacon of crimson that has made it an unmistakable sight in our night sky since the dawn of human consciousness. This visceral, blood-red appearance was not lost on the ancients. The early sky watchers, from the Babylonians to the Egyptians, noted its fiery aspect. It was the Romans, however, whose nomenclature would endure through history. Gazing upon this baleful point of light that wandered against the backdrop of the fixed stars, they saw an omen of conflict, a celestial embodiment of strife and battle. And so they named it after their own revered and feared god of war, Mars. The name was a perfect fit, a title that captured the planet's aggressive coloring and its seemingly unpredictable path across the heavens. While its name speaks of myth and legend, its physical dimensions are a matter of precise scientific measurement. Mars is not a perfect sphere. Like many rotating bodies, it bulges slightly at its equator. This equatorial diameter measures 6,792 kilometers, a substantial distance of about 4,220 miles. From pole to pole, however, the planet is slightly flattened, with a polar diameter of 6,752 kilometers, which is roughly 4,196 miles. While these numbers seem vast on a human scale, they reveal a world with a mass that is only about 11% of Earth's. In terms of sheer heft and gravitational influence, our own world is substantially more massive, a fact that has profound implications for everything from atmospheric retention to the physiology of any potential human visitors. The planet is, in essence, about half the size of Earth, a smaller, less dense sibling. Yet this simple comparison of size conceals a fascinating and counterintuitive truth about its surface. Despite its diminished stature, Mars possesses an amount of dry land that is remarkably similar to the total landmass of Earth. This seeming paradox is resolved not by looking at Mars, but by considering the defining feature of our own planet, its vast, deep oceans. Roughly 2/3 of Earth's surface is submerged beneath water, a global sea that hides the majority of our planet's solid crust. Mars, on the other hand, is a desiccated desert world. It has no oceans, no seas, no significant bodies of standing liquid water to claim its territory. As a result, its entire surface is exposed land, a continuous expanse of craters, volcanoes, and plains that, when summed together, offer a terrestrial area for exploration that rivals all of Earth's continents combined. The temporal rhythms of Mars are at once familiar and alien. It spins on its axis at a rate remarkably close to that of Earth, completing a full rotation in 24.6 hours. This Martian day, designated by scientists as a sol to avoid confusion with our own 24-hour cycle, means that a day spent on its surface would feel uncannily familiar in its length. The sun would rise and set in a pattern that would not be jarringly different from the one we experience. However, while its daily spin is familiar, its yearly journey is a far grander and more protracted affair. Orbiting the Sun at a greater distance than Earth, Mars takes significantly longer to complete one full circuit. A Martian year stretches on for 687 Earth days, making it nearly twice as long as our own. This extended orbital period has a profound effect on its seasons, which are not only longer, but also more varied in their duration due to the planet's more elliptical path. This extended Martian year is governed by the same celestial mechanics that dictate the seasons on Earth, a rhythmic tilting of the planet's axis. Mars leans into its orbit at an angle of 25 degrees, a tilt so remarkably similar to Earth's own 23.5-degree inclination that it establishes a familiar pattern of summer, autumn, winter, and spring. As the planet journeys around the Sun, one hemisphere is angled more directly towards the life-giving star, basking in more concentrated sunlight and experiencing summer, while the other hemisphere is angled away, receiving slanted, weaker rays and enduring the chill of winter. This axial tilt is the fundamental engine of the seasons, a cosmic nod that creates a cycle of warmth and cold, of growing and shrinking polar ice caps. This similarity in tilt, however, conceals a crucial difference in the shape of Mars's journey, a distinction that dramatically alters the character and duration of its seasons. While Earth's orbit is a nearly perfect circle, Mars follows a more elongated, elliptical path. This eccentricity means that its distance from the Sun varies much more significantly throughout its long year. At its closest point, or perihelion, Mars is about 128 million miles, or 206 million kilometers, from the Sun. At its most distant point, aphelion, it recedes to about 154 million miles, or 249 million kilometers. This immense variation in distance combines with the axial tilt to create seasons of unequal length and intensity. The planet moves fastest in its orbit when it is closest to the Sun, and slowest when it is farthest away, a direct consequence of the laws of orbital mechanics. The result is a climate system of extremes. The longest season on Mars is spring in the northern hemisphere, a leisurely period that stretches for a remarkable 194 sols. This is followed by a northern summer of 178 sols. In contrast, the shortest season is autumn in the northern hemisphere, which lasts for only 142 days. This asymmetry means that southern hemisphere summers are short and hot, occurring when Mars is closest to the Sun, while its winters are long and bitterly cold. The experience of being on the surface of this world would be profoundly different, beginning with the very force that holds you to the ground. The surface gravity on Mars is a mere 38% of what we experience on Earth. This radical reduction in gravitational pull would transform every physical action into something new and effortless. A simple step would feel like a bound, and a person could leap nearly 3 times higher than they could on Earth. hanging in the thin air for a moment before slowly descending back to the dusty ground. This lightness would be reflected in your physical weight. An individual who weighs 100 pounds, or about 45 kilograms, on Earth would find their weight reduced to a mere 38 pounds, or just over 17 kilograms, on the scales of Mars. Every piece of equipment, every rover, every future habitat would be subject to this same gentle pull, a factor that both simplifies certain engineering challenges and introduces new physiological ones for long-term human explorers. Looking upward from this low-gravity world reveals a sky that is both haunting and beautiful, and utterly unlike our own. The sun, the familiar anchor of our own sky, would appear strangely diminished. Because Mars orbits so much farther from the star, the solar disk in the Martian sky would seem only about half the size it does from Earth, a more distant and less generous source of light and warmth. This shrunken star presides over a sky whose colors defy our terrestrial expectations. During the day, the heavens are not a deep, familiar blue, but rather a hazy, pinkish red, a perpetual twilight that has been described as a butterscotch or salmon color. This strange hue is a direct result of the planet's atmosphere, or rather, the contents within it. Then, as the distant, small sun sinks toward the horizon, the sky does not erupt in the fiery reds and oranges of an earthly twilight. Instead, a serene and ghostly spectacle unfolds. The area immediately around the solar disk begins to glow with a deep, ethereal blue. This Martian blue sunset is one of the most visually stunning phenomena in the solar system, a moment of profound, alien beauty. The reason for this surreal optical display, for both the pinkish days and the blue evenings, lies in the nature of the Martian air itself. Mars possesses a very thin atmosphere, a fragile and tenuous veil of gas that is about 100 times less dense than the air we breathe on. Earth. On our planet, the sky is blue because the nitrogen and oxygen molecules in our thick atmosphere are very small and are particularly good at scattering short wavelength blue light in all directions, a phenomenon known as Rayleigh scattering. On Mars, however, the atmosphere is so thin that the gas molecules themselves play a minor role. Instead, the air is filled with fine particles of that ubiquitous red iron oxide dust kicked up from the surface by winds. These dust particles are much larger than air molecules and scatter light differently. They tend to scatter red light forward in the same direction as the sun's rays, which is why the daytime sky takes on its reddish-pinkish hue. But at sunset, as the sunlight travels through a much greater length of the dusty atmosphere, most of the red light is scattered away from the observer's direct line of sight, allowing the blue light to penetrate through more directly, creating that hauntingly beautiful azure glow around the setting sun. This incredibly thin atmosphere is the key to understanding so much about Mars. It is a whisper of a climate system, a ghost of the thicker, warmer atmosphere the planet may have once possessed. The character of this thin, pinkish sky is dictated by its very composition, a mixture of gases that is profoundly alien to our own life-giving air. The Martian atmosphere is primarily composed of carbon dioxide, accounting for a staggering 95% of its volume. This makes it an asphyxiating environment for humans, a stark contrast to Earth's atmosphere, which is dominated by nitrogen and contains the precious 21% oxygen we need to survive. The remaining slivers of the Martian air are made up of small amounts of nitrogen and argon, with only trace amounts of other gases. This overwhelming dominance of carbon dioxide is a crucial clue to the planet's history, suggesting a world where volcanic outgassing once filled the air with this heavy gas, but where no biological or geological processes, like the ones on Earth, ever emerged to transform it into something else. This thin blanket of gas is utterly incapable of trapping the sun's heat, leading to wild and unforgiving temperature fluctuations that define the daily life of the planet. Without a substantial atmospheric buffer, the energy from the sun that strikes the Martian surface during the day radiates straight back out into the coldness of space as soon as night falls. This results in a thermal whiplash of incredible proportions. In the depths of a polar winter, temperatures can plunge to a truly frigid -153 degrees Celsius, which is about -2 degrees Fahrenheit, 143 degrees Fahrenheit. Yet, on a warm summer day at the equator, the temperature of the surface itself can rise to a more moderate 20 degrees Celsius, or a comfortable 68 degrees Fahrenheit. This immense range, from a pleasant afternoon to a cold far exceeding anything in Antarctica, can occur in a single location over the course of a Martian year, creating one of the most hostile and unstable thermal environments in the solar system. This atmospheric stripping and climate collapse is exacerbated by another critical absence that lies deep within the planet itself. Mars lacks a global magnetic field. Unlike Earth, which has a molten iron core that generates a powerful magnetosphere, Mars's core has largely solidified. This protective magnetic bubble is what shields Earth's atmosphere from the solar wind, a constant stream of charged particles flowing from the sun that would otherwise scour our air away into space. Mars, without this global shield, has had its atmosphere steadily eroded over billions of years, thinning it out to its current fragile state. Curiously, however, Mars is not entirely magnetically dead. Instead of a planet-wide field, scientists have found localized pockets of intense magnetism locked into the ancient crust, particularly in the southern hemisphere. These magnetic anomalies are like ghostly echoes of a distant past, fossilized remnants from a time more than 4 billion years ago, when Mars was a younger, hotter world with a churning, molten core and a protective global magnetosphere. When the core cooled and the dynamo died, these patches of the crust retained the magnetic alignment they had at the time, leaving behind a strange and uneven magnetic landscape. At its heart, Mars is a terrestrial planet, a member of the inner solar system's family of solid, rocky worlds, alongside Earth, Venus, and Mercury. This means it has a solid surface you could stand on, a world of rock and metal with a distinct internal structure of a core, mantle, and crust. This rocky surface is covered by a blanket of loose, fragmented material known as regolith. This is not soil in the earthly sense, as it contains no organic matter, but rather a deep layer of dust, broken rock, and other debris created by billions of years of meteorite impacts. This regolith is rich in the iron oxides that give the planet its signature color, and it is the material that our rovers have been diligently scooping, drilling, and analyzing for decades. As we pull our gaze away from the planet's surface and look to its immediate celestial neighborhood, we find that it is not alone. Mars is the lord of a tiny two-moon kingdom, attended by a pair of small, misshapen companions named Phobos and Deimos. For centuries, astronomers believed Mars to be moonless. It wasn't until the year 1877 that their existence was confirmed, a discovery made during a close opposition of Mars by the American astronomer Asaph Hall, using the powerful Great Equatorial Refractor Telescope at the United States Naval Observatory. Following classical tradition, Hall named his discoveries after the mythological attendants of the god of war. In the tales of ancient Greece, Ares, the counterpart to the Roman Mars, was accompanied into battle by his two sons, Phobos, the personification of fear, and Deimos, the personification of dread or panic. The names were a perfect, poetic fit for the tiny moons orbiting the war god's planet. The prevailing scientific theory is that these two small bodies are not original moons formed from the same material as Mars, but are instead captured asteroids. They are likely remnants from the asteroid belt that lies between Mars and Jupiter, wanderers that strayed too close to the red planet's gravitational influence and were ensnared in its orbit. Their composition, which is similar to that of carbonaceous asteroids, and their irregular shapes strongly support this hypothesis. And their shapes are indeed highly irregular. They are not the grand, spherical orbs we associate with major moons, like our own. Instead, they are lumpy and cratered, having the distinct appearance of cosmic potatoes. Their irregular, potato-like shape is a direct consequence of their diminutive size. They are simply not massive enough for their own gravity to be strong enough to overcome the structural integrity of their rock and pull them into a state of hydrostatic equilibrium, the process that forces larger celestial bodies into a nearly perfect sphere. Phobos and Deimos are ancient, battered relics, captured wanderers that bear silent witness to the long and tumultuous history of their adoptive parent planet. The celestial dance of these two captured asteroids is a tale of two very different fates, a cosmic drama playing out over immense timescales. Phobos, the larger and inner of the two moons, the embodiment of fear, is locked in a slow, inexorable death spiral. It orbits Mars at an astonishingly close distance, a mere 6,000 kilometers, or about 3,700 miles, above the planet's surface. This proximity is its undoing. The powerful gravitational pull of Mars is constantly tugging at Phobos, creating tidal forces that are drawing it ever closer. Each century, the moon creeps about 2 meters, or 6.5 feet, nearer to the rust-colored world below. This gravitational embrace is slowly tightening, and scientists predict that in about 50 million years, this process will reach its dramatic and violent conclusion. One of two scenarios will unfold. Phobos will either be torn apart by the relentless Martian gravity, its rocky body disintegrating into a cloud of debris that will form a new, spectacular ring system around the planet, or it will survive this tidal shredding only to ultimately collide with Mars in a cataclysmic impact event. Deimos, the smaller and more distant moon, the personification of panic, is on a much different trajectory. It orbits far beyond Phobos, at a distance of over 23,000 kilometers, or 14,000 miles, and is thus subject to a much weaker gravitational pull. Unlike its doomed sibling, Deimos is slowly, almost imperceptibly, drifting away from Mars. Its orbit is gradually expanding, and it is destined to one day escape the planet's grasp entirely, to be cast back out into the void of space, to wander the solar system once more. Back on the surface of Mars itself, we find a world of geological superlatives, a landscape carved on a scale that dwarfs anything on Earth. Here, rising from the Tharsis volcanic plateau, stands the largest volcano in the entire solar system, Olympus Mons. This is not merely a mountain. It is a geological feature of such immense proportions that it defies easy comparison. Olympus. Mons stands at a staggering height of about 22 kilometers, or 13.6 miles, from its base to its summit caldera. This makes it nearly 3 times taller than Mount Everest, our own planet's highest peak. Its base is so vast, spanning some 600 kilometers, or 370 miles, in diameter, that an observer standing on its slopes would not even perceive the curvature of the volcano. The horizon would simply appear as a flat plain stretching out before them. This colossal shield volcano was able to grow to such a monumental size because of a key difference in Martian geology. Unlike Earth, Mars does not have active tectonic plates. On our planet, the crust is constantly shifting over volcanic hotspots, which means that volcanoes are carried away from their magma source, limiting their growth. On Mars, the crust is stationary. For hundreds of millions of years, the hotspot that fed Olympus Mons remained in a fixed position, allowing lava to build up in the same spot, layer upon layer, creating a mountain of truly planetary proportions. As if one such feature were not enough, Mars also boasts the most extensive and deepest canyon system in the solar system, a vast network of interconnected chasms known as valles marineris. This is not a single canyon, but a sprawling complex of gorges that was first imaged in detail by the Mariner 9 spacecraft in the early 1971. Valles Marineris stretches for over 4,000 kilometers, or 2,500 miles, along the Martian equator. If it were on Earth, it would span the entire width of the continental United States, from New York City to Los Angeles. In places, the canyon plunges to depths of up to 11 kilometers, or 7 miles, dwarfing our own Grand Canyon, which is a mere 1.8 kilometers, or just over a mile, deep at its lowest point. Its width is equally breathtaking, reaching up to 600 kilometers, or 370 miles, across in some regions. Unlike the Grand Canyon, which was carved by the relentless erosive power of the Colorado River over millions of years, Valles Marineris is primarily a tectonic feature. It is a massive rift in the Martian crust, a gigantic crack that likely formed as the planet cooled and the nearby Tharsis volcanic region bulged upwards, stretching and fracturing the surrounding lithosphere. This initial tectonic rift was then widened and shaped by massive landslides, and possibly by the outflow of subsurface water. The planet's surface is marked by a profound and mysterious division, a stark contrast between its two halves that is known as the Martian crustal dichotomy. The northern hemisphere of Mars is characterized by its remarkably smooth, flat lowlands, vast plains that have been resurfaced by ancient lava flows and show very few impact craters. This region, sometimes called the Borealis Basin, sits at a much lower elevation than the south. In stark contrast, the southern hemisphere is a rugged, ancient landscape. It is dominated by heavily cratered highlands, a testament to its immense age and its long exposure to the bombardment of asteroids and comets during the early, violent history of the solar system. This fundamental difference between the two hemispheres is one of the planet's greatest unsolved mysteries. The leading hypothesis suggests that the smooth northern lowlands are, in fact, the remnants of a single, colossal impact event. The Borealis Basin is thought to be the largest confirmed impact crater in the solar system, a scar left by a collision with a protoplanet-sized object, perhaps as large as Pluto, that struck Mars more than 4 billion years ago. This titanic impact would have obliterated the original crust of the northern hemisphere, creating a vast basin that was later filled in by volcanic activity, resulting in the smooth plains we see today. Within these cratered southern highlands, we find another immense impact feature, the Hellas Planitia. While not as vast as the Borealis Basin, it is still a feature of immense scale. This giant circular basin, located in the southern hemisphere, is over 6 kilometers, or 3.7 miles, deep and stretches for 2,000 kilometers, or 1,242 miles, in diameter. It is one of the largest and oldest visible impact craters in the solar system, a deep bowl that contains the lowest elevations on the entire Martian surface. Etched into the ancient, cratered surfaces of Mars is a ghost of a very different past, a tantalizing and widespread network of features that speak of a warmer, wetter world. Across the planet, but particularly in the older southern highlands, we find numerous channels, valleys, and gullies that bear an uncanny resemblance to the riverbeds of Earth. These sinuous, branching networks look for all the world as if they were carved by the persistent flow of liquid water over immense geological timescales. Some of these features are massive outflow channels, suggesting catastrophic floods on a scale that beggars belief, while others are delicate, dendritic valley networks that seem to have been formed by the slow, patient work of rainfall and surface runoff, much like the river systems that drain our own continents. This compelling visual evidence strongly suggests that billions of years ago, Mars had a thicker atmosphere, higher temperatures, and, most importantly, stable liquid water flowing freely across its surface. This vision of an ancient, water-rich Mars is further solidified by the presence of vast, layered polar ice caps, one of the planet's most dynamic and visually striking features. At both the north and south poles lie enormous deposits of ice. These are not composed solely of water ice, as are Earth's polar caps, but are a complex, layered mixture of both water ice and frozen carbon dioxide, more commonly known as dry ice. The permanent northern polar cap, known as the Planum boreum, is about 1,000 kilometers, or 620 miles, in diameter, and consists mostly of water ice, with a thin, seasonal veneer of carbon dioxide ice. The southern cap, the Planum australe, is smaller and has a permanent core of water ice that is covered by a much thicker, year-round layer of carbon dioxide ice. These magnificent ice deposits are not static. They are a living, breathing part of the Martian climate system. They visibly expand and contract with the changing Martian seasons, a rhythmic pulse driven by the planet's long, elliptical orbit. During the Martian winter, as temperatures plummet, carbon dioxide from the atmosphere freezes out and deposits onto the polar cap, causing it to grow significantly. In fact, up to a third of the entire Martian atmosphere can be locked away in the form of dry ice during the peak of winter. Then, as spring arrives and sunlight returns to the pole, the frozen carbon dioxide sublimates, turning directly from a solid back into a gas, and the ice cap recedes, releasing the gas back into the atmosphere and causing a corresponding rise in atmospheric pressure across the planet. This seasonal cycle of freezing and thawing is the most dramatic and influential climatic process happening on Mars today. While the bulk of Mars's water is now locked away in these polar caps, tantalizing evidence suggests that liquid water may still exist in hidden reservoirs beneath the surface. Orbiting spacecraft using ground-penetrating radar have detected signs of what appear to be large bodies of salty, liquid water, or brines, trapped beneath the southern polar ice cap. The presence of salts would be crucial, as they would significantly lower the freezing point of the water, allowing it to remain in a liquid state even in the extreme cold of the Martian subsurface. These potential subglacial lakes are of immense interest to astrobiologists, as they represent one of the most promising environments where microbial life could potentially survive on Mars today, shielded from the harsh surface radiation and extreme temperatures. The surface itself is a museum of aquatic history, preserving clear and unambiguous signs of its watery past. Orbital images have revealed ancient riverbeds that meander for hundreds of kilometers, deltas where these rivers deposited sediment as they emptied into what were once vast lakes or even oceans, and the unmistakable shorelines of these long vanished bodies of water. The rovers on the ground have added to this picture, discovering water-lane sedimentary rocks, clay minerals that can only form in the presence of water, and spherical concretions, nicknamed blueberries, that are another telltale sign of a once wet environment. Certain geological features on Mars are so vast and dramatic that they hint at a past not just of gentle rivers and lakes, but of unimaginable, catastrophic floods. About 3.5 billion years ago, it appears that massive amounts of groundwater, perhaps stored beneath a thick layer of permafrost, were suddenly and violently released onto the surface. These megafloods would have been orders of magnitude larger than any flood known on Earth, events that would have reshaped the entire landscape in a matter of weeks, carving out the immense outflow channels that we see today and pouring vast quantities of water into the northern lowlands. Despite this compelling evidence for a wet past, the current conditions on Mars make it impossible for liquid water to remain stable on the surface for any significant length of time. The culprit is the planet's incredibly thin atmosphere. The atmospheric pressure on Mars is less than 1% of Earth's, a near vacuum. At such low pressures, water has a very low boiling point. Any pure liquid water that might somehow appear on the surface would instantly and violently boil away, even at temperatures well below freezing. This thin air, coupled with the frigid temperatures, means that water on Mars can typically only exist as a solid, ice, or as a gas, water vapor. There is a potential loophole, however. If the water were extremely salty, forming a brine, its freezing point would be lowered and its boiling point would be raised. This would make it theoretically possible for these brines to exist in a liquid state for short periods, under specific temperature and pressure conditions in certain locations on the surface. Indeed, recurring slope lineae, dark streaks that appear on some crater walls during the warmest months, are thought by some scientists to be evidence of the seasonal flow of these salty brines. While its water is now mostly hidden or gone, Mars is far from a static, quiescent world. It is a planet of wind, a world scoured by massive, planet-engulfing dust storms that are legendary throughout the solar system. These storms are a regular feature of the Martian climate, typically occurring during the southern hemisphere's spring and summer, when the planet is closest to the sun and surface heating is at its maximum. While most are localized events, every few years a regional storm will grow and coalesce with others, erupting into a global event that can shroud the entire planet in a thick, impenetrable haze of red dust for weeks or even months on end. These planetary-scale dust storms are the largest and most violent in the entire solar system. Once initiated, they are powered by a feedback loop, where the dust lifted into the atmosphere absorbs sunlight, warming the surrounding air, which in turn creates stronger winds that lift even more dust, a process that can quickly escalate into a global phenomenon. These storms pose a significant threat to robotic and future human exploration, blocking sunlight from reaching solar panels and creating a hazardous, dusty environment. The winds that drive these epic storms are themselves a force to be reckoned with. While the thin Martian air means that the pressure exerted by the wind is much lower than on Earth, the wind speeds themselves can be extreme. Within the heart of a major dust storm, wind speeds can reach up to 125 miles per hour or 200 kilometers per hour. While you wouldn't be knocked over by this wind due to the low atmospheric density, it is more than capable of lifting vast quantities of fine dust particles high into the atmosphere, creating the spectacular and planet-altering storms for which Mars is famous. Even on a calm Martian day, when the global dust storms are dormant, the wind makes its presence known in a more localized and elegant form. The dust devil. These are a frequent and captivating sight on the Martian surface, swirling columns of dust that dance across the arid plains. Much like their counterparts in the deserts of Earth, Martian dust devils are formed by solar heating of the ground, which creates a pocket of hot, rising air. As this thermal plume ascends, it can begin to rotate, picking up loose surface dust and creating a miniature vortex, a spinning, towering funnel of red grit that can range from a few meters to over a kilometer in height. For years, these were only observed from orbit, seen as faint, snake-like tracks left in the dust. But with the arrival of landers and rovers, we have been able to witness them up close, capturing stunning images and even recordings of their ghostly, whispering passage. These dust devils play a surprisingly important role in the Martian climate. They are a key mechanism for lifting dust into the thin atmosphere, contributing to the overall dust load that gives the sky its characteristic pinkish hue. They also perform an unexpectedly useful service for our robotic explorers. On several occasions, a passing dust devil has serendipitously swept the accumulated red dust off the solar panels of rovers like Spirit and Opportunity, effectively cleaning them and providing a welcome boost in power that significantly extended their operational lives. Our understanding of these intricate phenomena, from the subtlest winds to the grandest geological features, is the result of a long and arduous journey of observation and exploration. A story that begins with the first human to point a telescope at the red planet. That pioneer was the Italian astronomer Galileo Galilei, who, in the year 1610, turned his revolutionary new instrument towards Mars. While his early telescope was too primitive to reveal any surface details, he was the first to see it not as a mere point of light, but as a distinct disk, a true world in its own right. This simple observation forever shattered the ancient concept of the planets as perfect, ethereal orbs and opened the door to their study as physical places. The view of Mars became dramatically clearer over the subsequent centuries, culminating in the late 19th century with the work of the American astronomer Percival Lowell. From his purpose-built observatory in Flagstaff, Arizona, Lowell spent years meticulously sketching the Martian surface. In the faint, shimmering details he could resolve, he became convinced that he saw a complex network of long, straight lines crisscrossing the planet's lighter and darker regions. He famously, and mistakenly, interpreted these features as artificial canals, vast engineering works built by a sophisticated, intelligent Martian civilization to channel water from the polar ice caps to the dying desert cities of the equator. Lowell's theories, published in a series of popular books, electrified the public imagination and firmly cemented the idea of Mars as the abode of intelligent life in the cultural consciousness, a powerful myth that would persist for decades and inspire a generation of science fiction writers. The dream of Martian civilizations was finally put to rest with the dawn of the space age, which replaced romantic speculation with hard and often disappointing data. The very first successful mission to Mars was the United States Mariner 4 spacecraft, which flew past the planet in the summer of 1964. It returned just 22 grainy black and white images, but they were revolutionary. They revealed a stark, cratered surface that looked more like the moon than the Earth, with no signs of canals, cities, or life. It was a profound moment of discovery, a first sobering glimpse of the real Mars. The true golden age of Martian robotic exploration began decades later with the arrival of a new kind of explorer, the rover. The first truly successful and transformative rovers were the twin robots of NASA's Mars Exploration Rover mission, Spirit and Opportunity. They landed on opposite sides of the planet in January of 2004, embarking on a mission that would rewrite the textbooks on Martian geology. These golf cart-sized, solar-powered geologists were tasked with a simple but profound objective: to search for evidence of past water activity on Mars. Their success was nothing short of astonishing. Both rovers found a wealth of evidence for a watery past, from rocks that clearly formed in water to minerals like hematite and gypsum that are telltale signs of ancient lakes and hot springs. The Spirit rover, in particular, had a mission of extraordinary longevity. Designed for a primary mission of just 90 days, this tenacious robot defied all expectations, continuing to explore, analyze, and transmit data for more than 6 years. It roamed across the plains of Gusev Crater, climbed the Columbia Hills, and survived brutal dust storms and frigid winters, a testament to the resilience and ingenuity of its creators. Its long journey finally ended in 2010 when it became stuck in a patch of soft soil, its mission silenced by the harsh Martian winter. The baton of exploration was then passed to a new generation of rover, a machine of unprecedented size and capability: Curiosity. This car-sized, nuclear-powered mobile laboratory landed in Gale Crater in August of 2012, carrying a sophisticated suite of scientific instruments designed to assess the past and present habitability of Mars. Curiosity's primary mission was to determine whether Mars ever had the right environmental conditions to support microbial life. Drilling into rocks and analyzing their chemical composition, it has made a series of groundbreaking discoveries. In 2018, a landmark discovery was announced, not from Curiosity on the surface, but from the European Space Agency's Mars Express orbiter. Using its MAR-SIS ground-penetrating radar instrument, scientists found compelling evidence of a large body of liquid water. A lake roughly 20 kilometers or 12 miles across, buried 1.5 kilometers or about a mile beneath the ice of the southern polar cap. This was a monumental finding, the first detection of a stable, persistent body of liquid water on modern Mars, and it instantly became a prime target in the search for extraterrestrial life. The current vanguard of Martian surface exploration is the Perseverance rover, the 5th NASA rover to successfully land on the planet. It touched down in Jezero Crater in February of 2021, a site specifically chosen because it was once a river delta, a place where water flowed into an ancient lake, making it a prime location to search for signs of past microbial life or biosignatures. Perseverance is not just a geologist. It is the first stage of an ambitious plan to bring pieces of Mars back to Earth. Its core mission is to drill into the most promising rocks and seal pristine samples of the Martian surface in special tubes, which will be left in a cache on the surface for a future mission to retrieve and return to laboratories on our own world. A key and revolutionary component of the Perseverance mission was a small experimental technology demonstration that made history. Tucked into the rover's belly was the Ingenuity helicopter. In April of 2021, this tiny, lightweight aircraft made the first powered, controlled flight on another planet. Rising into the thin Martian air, it proved that aerial exploration of Mars was possible, opening up a whole new dimension for future missions. This remarkable feat, akin to the Wright brothers' first flight at Kitty Hawk, demonstrated a new way to explore other worlds, allowing future missions to scout ahead for rovers, explore otherwise inaccessible terrain like cliffs and canyons, and provide a unique aerial perspective of the Martian landscape. The story of these robotic triumphs, however, is set against a much broader and more sobering backdrop of immense difficulty and frequent failure. Mars has earned a reputation as a veritable graveyard of spacecraft, a challenging destination that has thwarted numerous attempts at exploration. As of September 2014, a total of 40 missions had been launched towards the Red Planet by various space agencies around the world. Of that ambitious armada of orbiters, landers, and rovers, only a mere 18 were ultimately successful in achieving their primary objectives. This high failure rate, a stark reminder of the immense technical challenges of interplanetary travel, has been attributed to everything from launch vehicle malfunctions and communication errors to the complex and perilous process of entering the Martian atmosphere and landing safely on its surface. The journey itself is a long and arduous one, a cosmic voyage across the vast expanse of space that separates our world from Mars. A trip from Earth to Mars is not a straight line, but a carefully calculated trajectory known as a Hohmann transfer orbit, which is the most fuel-efficient path between two planets. This elliptical journey, coasting on the momentum of its launch, takes approximately 8 months to complete. During this long transit, the spacecraft is exposed to the harsh environment of deep space, including cosmic radiation and extreme temperature swings, all while its systems must remain perfectly operational for the critical arrival and insertion into Martian orbit, or the harrowing descent to the surface. Our very first visual reconnaissance of the planet, the initial glimpse that began to replace speculation with fact, came from the aforementioned Mariner 4 mission. In July of 1965, after its long interplanetary cruise, the spacecraft flew past Mars and transmitted the first close-up pictures ever taken of another planet from deep space. These 22 images, transmitted at a painfully slow rate of 8 1/3 bits per second, took hours to receive and process. The resulting photographs, grainy and lacking in detail by modern standards, were nonetheless a revelation. They depicted a cratered, moon-like surface, a far cry from the vibrant, living world that Lowell had envisioned, and they marked the true beginning of our scientific exploration of the planet. A few years later, in 1971, another NASA spacecraft, Mariner 9, achieved a major milestone by becoming the first artificial satellite to successfully orbit another planet. Arriving at Mars during a massive planet-encircling dust storm that obscured the entire surface, the spacecraft patiently waited in orbit. As the dust began to settle over the next few months, Mariner 9 began its groundbreaking work. It proceeded to systematically map almost the entire surface of the planet in unprecedented detail, revealing the grand volcanoes of the Tharsis region, the immense gash of Valles Marineris, which was named in its honor, and the ancient, water-carved channels that hinted at a dramatically different past. Mariner 9 fundamentally changed our view of Mars from a static, cratered ball to a dynamic and geologically complex world. For decades, the exploration of Mars was a domain dominated by the United States and the Soviet Union. However, in recent years, the Red Planet has become a destination for a new generation of spacefaring nations. In a landmark achievement, China successfully landed its Zhurong rover on Mars in May of 2021. This made China only the second country, after the United States, to successfully operate a rover on the Martian surface. The Zhurong rover, named after a traditional Chinese fire god, landed in the vast northern plains of Utopia Planitia and began its own mission of studying the local geology and searching for signs of subsurface water ice, signaling a new era of international cooperation and competition in the exploration of Mars. The deep and abiding fascination with Mars is rooted in its very nature, a planet that is estimated to have formed alongside Earth and the other worlds of our solar system about 4.5 billion years ago. It is a sibling world, born from the same protoplanetary disk of gas and dust that swirled around the young sun. Its ancient rocks and dust therefore hold crucial clues, not just to its own history, but to the formation and evolution of our entire solar system. In a remarkable gift from the cosmos, we haven't always had to travel to Mars to study it. On rare occasions, pieces of Mars have come to us. Over the eons, major asteroid impacts on the Martian surface have had enough energy to blast chunks of rock into space with escape velocity. After wandering in the solar system for millions of years, a small number of these rocks have eventually fallen to Earth as meteorites. These Martian meteorites, identifiable by the unique composition of gases trapped in tiny pockets within them, which perfectly match the Martian atmosphere as measured by our landers, are invaluable scientific treasures. They have provided scientists with tangible samples of the red planet that can be studied in laboratories with a level of detail and sophistication far beyond what is possible with robotic rovers. These precious fragments have allowed scientists to study the planet's mineralogy, geochemistry, and even its atmospheric history long before the first space missions were ever launched. They are a direct physical link between our world and the plains of Mars. This ability to study Mars, whether through meteorites or telescopes, is aided by the fact that it is one of our closest planetary neighbors. Mars is one of the 5 planets, along with Mercury, Venus, Jupiter, and Saturn, that are bright enough to be visible from Earth with the naked eye, without the need for a telescope. Its distinct, steady, reddish glow has made it a familiar and easily recognizable object in the night sky for cultures all over the world since the dawn of human history. It has been a constant presence in our heavens, a wandering star that has inspired myth, religion, and science in equal measure. This proximity, combined with its tantalizing similarities to our own world, has made Mars the most compelling and logical target for the next great leap in human exploration. Of all the planets in our solar system, Mars is considered the most likely and promising destination for future human exploration, and perhaps one day, colonization. While it is a harsh and unforgiving environment, it is far more hospitable than the crushing pressures and searing heat of Venus or the frigid, gas giant worlds of the outer solar system. It has a solid surface, a day-night cycle similar to Earth's, a supply of water ice, and an atmosphere, however thin, that could potentially be used to manufacture resources like oxygen and rocket fuel. For these reasons, Mars looms large in the plans of space agencies and private companies, representing the next frontier for humanity, a place where we might one day establish a permanent, self-sustaining presence beyond our home world. The deep, almost primal connection between Mars and humanity is woven into the very fabric of our culture, extending even to the way we mark the passage of time. The name of the 3rd month of the Gregorian calendar, March, is a direct linguistic inheritance from the ancient Romans. The Roman year originally began in the spring with the month of Martius, named in honor of their god of war, Mars. This was a logical association, as the end of winter signaled the resumption of both agricultural activities and military campaigns, both of which were under the patronage of the powerful deity. As the Roman calendar evolved and was eventually adopted and modified throughout Europe, the name persisted, leaving us with a permanent, yearly reminder of the red planet's enduring influence on Western civilization. To truly grasp the scale of the solar system and Mars's place within it, it is helpful to step away from the abstract astronomical numbers and create a more tangible model. Imagine a scale model where the Sun, our system's immense central star, is shrunk down to the size of a typical front door. In this miniature cosmos, our own planet, Earth, would be the size of a dime, a small, shining coin orbiting at a distance of about 1 city block from the front door sun. Following this same scale, Mars would be the size of a common aspirin tablet. This tiny, reddish speck would be orbiting about 1.5 blocks away from the sun, a noticeably more distant and smaller world than our own. This simple analogy powerfully illustrates the vast, empty distances of the inner solar system and the relatively diminutive size of the terrestrial planets compared to the star they orbit. A critical and life-threatening aspect of the Martian environment is the composition of its atmosphere, which, as we've seen, is overwhelmingly carbon dioxide. Complementing this is a profound lack of the one gas essential for human and animal life: oxygen. There is very little free oxygen in the Martian atmosphere, amounting to only about 0.1% of the total volume. This is a stark contrast to Earth's air, which is a rich and life-sustaining 21% oxygen. This absence means that any future human explorers on Mars would be entirely dependent on manufactured life support systems. They would have to live in sealed habitats and wear spacesuits with their own self-contained oxygen supply every time they ventured outside. However, this challenge also presents an opportunity. The abundant carbon dioxide in the Martian air is a valuable resource. Through a process of electrolysis, it is possible to split the carbon dioxide molecules, CO2, into carbon monoxide, CO, and breathable oxygen, O2, a technology that is being tested on the Perseverance rover with an instrument called MOXIE. This process, known as in situ resource utilization, could one day allow future Martian colonists to live off the land by manufacturing their own breathable air and rocket propellant from the local atmosphere. One of the most tantalizing and persistent mysteries on Mars revolves around the detection of another gas, present in only minuscule trace amounts: methane. On Earth, the vast majority of atmospheric methane is produced by biological processes, from microbes in wetlands to the digestive systems of livestock. Its presence in the Martian atmosphere, first confirmed by Earth-based telescopes and later by orbiting spacecraft and the Curiosity rover, is therefore a source of intense scientific excitement and debate. The detection of methane on Mars is a significant mystery for scientists because it is a chemically unstable gas that should be broken down by ultraviolet sunlight in a few hundred years. This means that if it is present in the atmosphere, there must be an active, ongoing source that is replenishing it. There are two main possibilities for this source. The first, and most thrilling, is that the methane is being produced by subsurface microbial life, tiny Martian organisms that could be surviving in underground pockets of liquid water, releasing methane as a waste product. The second, more mundane but still fascinating possibility, is that the methane is the result of ongoing geological activity. A process called serpentinization, which involves the interaction of water with certain types of rock, can produce methane without the need for life. The mystery deepened when it was discovered that the methane concentrations appear to vary seasonally and are found in localized plumes, suggesting a source that is periodically active. Pinpointing the origin of this Martian methane is now one of the highest priorities in planetary science, as it could be the first credible biosignature we have ever found on another world. The quest to reach and understand Mars has inspired not just scientists and engineers, but a global community of advocates and enthusiasts who are passionate about the future of humanity in space. One of the most prominent of these groups is the Mars Society, a non-profit organization that was founded in the year 1998. Its mission is to actively and publicly advocate for the human exploration and eventual settlement of the planet Mars. The Society, led by its founder, Robert Zubrin, promotes the idea that a human presence on Mars is a desirable and achievable goal for our civilization. They organize conferences, run public outreach campaigns, and operate simulated Mars research stations in remote Mars-like locations on Earth, such as the deserts of Utah and the Canadian Arctic. These analog research stations allow teams of volunteers to live and work as if they were on Mars, testing equipment, developing procedures, and studying the psychological and social challenges of living in a small, isolated outpost, all in preparation for the day when humans finally set foot on the red planet. This grassroots enthusiasm was famously channeled into a highly publicized, though ultimately controversial, venture known as the Mars One project. This private initiative, launched in 2012, proposed an audacious and ambitious plan to establish the first permanent human colony on Mars, funded by a global media spectacle, including a reality television show that would document the selection and training of the astronauts. The project captured the public's imagination, receiving thousands of applications from people around the world who were willing to take a one-way trip to become the first Martian colonists. However, the Mars One project was met with widespread criticism and skepticism from the scientific and aerospace communities regarding its technical and financial feasibility. Experts pointed to a lack of credible mission architecture, unrealistic timelines, and a severe underestimation of the costs and complexities involved in such an undertaking. Ultimately, the project failed to secure the necessary funding and technology, and the company behind it went bankrupt, serving as a cautionary tale about the immense challenges that lie between the dream of settling Mars and the reality of making it happen. The very color of Mars, the deep, rusty red that so defines its character, has been a powerful and evocative symbol for civilizations throughout history. The red color of the planet was often and almost universally associated with blood, fire, and conflict by ancient cultures. This visceral connection made its naming after gods of war a common thread across many different societies. The ancient Greeks, who laid much of the foundation for Western astronomy, named the planet Ares, after their own powerful and often tempestuous god of war. Ares was a figure of violence, destruction, and the untamed, chaotic aspects of battle. And the blood-red star that bore his name was seen as a celestial reflection of his brutal nature. Similarly, in the cosmology of ancient China, the planets were associated with the 5 elements. Mars, with its fiery appearance, was logically referred to as the fire star, or Huo Xing. Its appearance was often watched closely by imperial astrologers, who believed its movements and brightness could foretell periods of conflict, upheaval, and dynastic change. The ancient Egyptians, with their long and sophisticated tradition of sky watching, also paid close attention to the red planet. Their priests and scribes gave Mars the name Herdesher, a simple and descriptive title which translates literally as the Red One. This celestial body was often associated with their god Horus, particularly in a form known as Horus of the Horizon, linking the red planet to one of their most important deities. This cross-cultural convergence on the theme of redness, fire, and war underscores the profound impact that this single visual characteristic has had on the human psyche for millennia. Beneath its uniform reddish hue, the planet Mars harbors a profound geological secret, a fundamental asymmetry that divides the world into 2 starkly different realms. This feature, known as the crustal dichotomy, is one of the most prominent and mysterious aspects of Martian geology. The northern and southern hemispheres of Mars possess distinctly different geological characteristics, creating a planet that is, in essence, 2 worlds fused into one. This is not a subtle variation. It is a dramatic and globally significant division that is immediately apparent on any topographical map of the planet. The northern hemisphere is a vast expanse of low-lying, smooth plains. This region is generally smoother and has a significantly lower elevation, on average several kilometers lower than the southern highlands. Its surface is relatively young, having been resurfaced by massive volcanic lava flows in the distant past, and as a result, it is marked by a much lower density of impact craters. This vast northern basin, as we've explored, is thought by many scientists to be the scar of a colossal, ancient impact that literally stripped away the original crust of that hemisphere. The southern hemisphere, in stark contrast, is a land of ancient, rugged terrain. It is characterized by its much higher elevation and is heavily cratered, a battered and pockmarked landscape that has faithfully recorded the intense period of bombardment that occurred early in the solar system's history. This ancient crust is significantly thicker than that of the northern lowlands. This hemispheric divide is a defining feature of the planet, and understanding its origin is a key goal of Martian science, as it holds the secret to the earliest, most formative events in the planet's life. While Mars today is a world without rings, this may not always be the case. Looking to its small moon, Phobos, we see the seeds of a future transformation. Mars does not currently have any rings, but it is predicted that its moon, Phobos, will eventually be torn apart by the planet's gravity. As the moon spirals ever closer, the tidal forces exerted by Mars will eventually exceed the moon's own gravitational cohesion, the force that holds it together. When it crosses this critical boundary, known as the Roche limit, Phobos will be shredded into a vast cloud of rock and dust. This debris will then spread out and settle into orbit around the planet's equator, forming a new and spectacular ring system. This dramatic event is predicted to occur in about 50 million years, and it will give Mars a celestial adornment similar to, though likely less grand than, the magnificent rings of Saturn. The planet's climate is a direct and unforgiving consequence of its wispy atmosphere. The thin atmosphere of Mars is not effective at retaining heat, a crucial function that a thicker atmosphere performs on Earth through the greenhouse effect. On our planet, gases like carbon dioxide and water vapor trap a portion of the sun's heat, keeping the surface warm enough to support liquid water and life. On Mars, this insulating blanket is almost non-existent. The sparse covering of carbon dioxide is simply too thin to trap any significant amount of solar energy. As a result, any heat that the surface absorbs during the day radiates almost immediately back into the blackness of space as soon as the sun sets, leading to the extreme daily temperature swings that are a hallmark of the Martian environment. This inefficient thermal regulation is a key reason why the planet is so cold and inhospitable today. This frigid nature of Mars gives rise to a unique and beautiful seasonal phenomenon. Every winter on Mars, as the pole in that hemisphere is plunged into months of darkness and extreme cold, a portion of the carbon dioxide in the atmosphere freezes and falls like snow, depositing a thin layer of carbon dioxide, frost, or dry ice directly onto the surface. This seasonal frost can extend from the poles down to the middle latitudes, blanketing the landscape in a delicate white layer. As spring returns, this dry ice layer sublimates, turning directly from a solid into a gas and returning to the atmosphere, a process that can create strange and beautiful erosion patterns on the surface, such as the spider-like arenaeform terrain found near the South Pole. Our modern, detailed understanding of Mars is built upon a legacy of pioneering missions that pushed the boundaries of technology and exploration. The first spacecraft to successfully land on the surface of Mars and conduct a sustained scientific mission were the twin Viking landers. In the summer of 1976, Viking 1 and Viking 2 touched down on the Martian plains, becoming the first probes to successfully operate on the planet's surface. They were stationary laboratories equipped with cameras that sent back the first color panoramas of the Martian landscape, a weather station that provided the first long-term meteorological data, and a robotic arm to scoop up soil samples. Most famously, they carried a suite of complex experiments designed to look for signs of microbial life in the Martian soil. While the results of these life detection experiments were ambiguous and are still debated by scientists today, the Viking missions provided a foundational dataset that revolutionized our understanding of Mars and laid the groundwork for all future surface missions. 2 decades later, a new era of mobility was ushered in with the arrival of the first NASA rover to land on Mars. This was the tiny, microwave oven-sized Sojourner rover, which was part of the Mars Pathfinder mission in 1997. Sojourner, named after the abolitionist and women's rights activist Sojourner Truth, was a technology demonstration designed to prove that roving on the Martian surface was possible. For 83 sols, it crept across the landscape surrounding its base station, analyzing the composition of nearby rocks and soil, and capturing the public's imagination with its plucky exploration. It was the first time a wheeled vehicle had ever been driven on another planet, and its resounding success paved the way for the larger, more ambitious rovers that would follow. While rovers explored the surface in detail, our broader global understanding of the planet has been driven by a fleet of powerful orbiters. The Mars Reconnaissance Orbiter, or MRO, has been one of the most productive of these missions. Since its arrival in orbit in 2006, not 2005, MRO has been studying the planet's atmosphere, surface, and subsurface with a suite of advanced instruments. Its most famous instrument is the High-Resolution Imaging Science Experiment, or HiRISE camera, which is capable of imaging the Martian surface with such stunning detail that it can resolve features as small as a dinner table. MRO's data has been instrumental in identifying future landing sites, studying geological processes like landslides and dust storms in action, and searching for evidence of water. While orbiters study the surface and atmosphere from above, a different kind of mission was needed to probe the planet's hidden interior. The InSight lander arrived on Mars in November of 2018 with a unique and focused mission: to study the planet's deep interior and seismic activity. The name InSight is an acronym for Interior Exploration, using seismic investigations, geodesy, and heat transport. Using an incredibly sensitive seismometer placed directly on the Martian surface, the lander has been listening for Marsquakes. By studying how the seismic waves from these quakes travel through the planet, scientists can deduce the structure and composition of the crust, mantle, and core, effectively giving Mars its first planetary checkup. This mission is providing the first detailed look at the internal architecture of another rocky planet, offering crucial clues about how terrestrial worlds form and evolve. The international effort to unravel the secrets of Mars has been significantly bolstered by the contributions of the European Space Agency, whose Mars Express orbiter has been a mainstay of Martian science for nearly 2 decades. Arriving in orbit around the Red Planet in 2003, this durable and highly successful mission has been systematically mapping the surface of Mars in high-resolution, 3-dimensional color. Its stunning images have been used to create global topographical maps and have provided a wealth of data on the planet's geology, mineralogy, and atmospheric composition. Mars Express was also the mission that carried the Marsis radar instrument, which provided the groundbreaking first evidence for the subglacial lake of liquid water beneath the southern polar ice cap. Its long and productive mission has provided a continuous and comprehensive dataset that has been a cornerstone of our modern understanding of the planet's history and evolution. The cumulative result of all this high-resolution mapping from both NASA and ESA orbiters is a detailed global portrait of a world that has been profoundly shaped by violence from above. We now know that there are at least 43,000 impact craters on Mars with a diameter of 5 kilometers or 3 miles or larger. This is merely a fraction of the total number of craters, which runs into the hundreds of thousands when smaller impacts are included. This immense crater count, particularly in the southern highlands, serves as a physical record of the planet's great age. It tells a story of a world that has been exposed to the rain of asteroids and comets for billions of years, without the benefit of a thick atmosphere to burn them up or active plate tectonics to erase their scars. Each crater is a fossilized explosion, a reminder of the chaotic and violent environment of the early solar system. As we look towards the future and seriously contemplate sending humans to this cratered world, we must confront the profound biological challenges posed by its environment. The low gravity on Mars, while perhaps enjoyable for short periods, could pose significant long-term health risks for astronauts. The human body is exquisitely adapted to the constant 1G environment of Earth. In the reduced 38% gravity of Mars, the loss of bone density and muscle mass, a condition similar to osteoporosis, would be a major concern. Without the constant stress of Earth's gravity, bones can become brittle and muscles can atrophy. Counteracting these effects would require rigorous daily exercise regimes and potentially new medical therapies to ensure the health and safety of astronauts on long-duration missions. Before we could send humans, however, early astronomers studied Mars from afar, piecing together its basic orbital characteristics. When observed from Earth through a telescope, Mars exhibits phases, much like our own moon. It can appear as a gibbous disk, but never as a thin crescent. This is a direct consequence of its orbit being outside of Earth's. We are looking at Mars from the inside, so to speak. We can see it when it is on the opposite side of the sun from us, when it is fully illuminated. And we can see it at various side angles, where it appears partially shadowed. However, because its orbit is exterior to ours, we can never see it in a position between the Earth and the Sun. The geometry required to see a crescent phase like that of Venus or Mercury. This simple observation was a key piece of evidence used by early astronomers like Copernicus to correctly deduce the structure of the solar system, with the Sun at the center. Our viewing opportunities of Mars are not constant. They follow a predictable celestial rhythm. The closest approach of Mars to Earth, an event known as a perihelic opposition, happens approximately every 26 months. This is the point in our respective orbits when Earth is directly between the Sun and Mars. And Mars is also near its closest point to the Sun, or perihelion. During these favorable oppositions, Mars appears at its largest and brightest in our night sky, offering the best opportunities for both amateur and professional astronomers to observe its surface details. It is during these launch windows, which also occur every 26 months, that missions to Mars are typically sent, as the journey requires the least amount of time and fuel. The history of Mars exploration is littered with cautionary tales, but none is more infamous or instructive than the failure of the Mars Climate Orbiter mission. In 1999, this NASA spacecraft was lost as it attempted to enter orbit around Mars. A subsequent investigation revealed a startlingly simple and entirely preventable error. The software on the ground, provided by one of the engineering teams, was calculating trajectory corrections using imperial units of measurement, specifically pound-seconds of force, while the spacecraft's own navigation software was programmed to expect those instructions in metric units, Newton seconds. This mix-up between the two measurement systems resulted in the spacecraft entering the Martian atmosphere at too low an altitude, causing it to burn up and disintegrate. The loss of this $125 million mission served as a stark and painful lesson for the entire aerospace industry about the critical importance of meticulous communication, double-checking, and the standardization of units in complex engineering projects. Despite its lack of a global magnetic field, Mars is not entirely without the beautiful, ethereal light shows known as auroras. On Earth, auroras are created when charged particles from the solar wind are funneled by our global magnetic field towards the poles, where they collide with atoms in the upper atmosphere, causing them to glow. On Mars, scientists have discovered aurora-like phenomena that occur not at the poles, but near the localized patches of strong magnetic fields locked in the crust of the southern hemisphere. These crustal magnetic anomalies can funnel solar wind particles down into the thin atmosphere above them, creating localized ultraviolet auroras that are invisible to the human eye, but have been detected by orbiting spacecraft. They are a beautiful and ghostly reminder of the planet's lost magnetic past. The flagship rover, Curiosity, has spent years methodically exploring the floor of Gale Crater, a 154-kilometer or 96-mile wide basin with a towering mountain of layered sediment at its center. Its exploration of this ancient crater has revealed definitive evidence of a past environment that was once surprisingly hospitable to life. The rover found fine-grained sedimentary rocks, clay minerals, and organic molecules, all of which point to the existence of an ancient, long-lived freshwater lake that once filled the crater floor. The chemistry of this lake, as analyzed by Curiosity's instruments, suggested that it could have once supported microbial life, possessing all the necessary chemical ingredients and a source of energy. This discovery was a landmark in the search for habitable environments beyond Earth. The ultimate goal of our current Martian exploration program is to one day bring pristine samples of the planet back to our laboratories. The Mars Sample. Return mission is a highly ambitious, multi-stage, collaborative effort between NASA and the European Space Agency. The first stage is already underway, with the Perseverance rover collecting and caching promising rock and soil samples. The next stages will involve sending a lander to Mars to pick up these samples, a small rocket to launch them into Martian orbit, and another spacecraft to capture the sample container in orbit and fly it back to Earth. This complex and audacious mission, planned for the next decade, would allow scientists to study Martian materials with the full power of Earth-based laboratories, potentially answering once and for all whether life has ever existed on Mars. Finally, as we contemplate a long-term human future on the Red Planet, a grand and controversial idea continues to be debated: the possibility of terraforming Mars. This is the hypothetical process of deliberately engineering the Martian environment to make it more hospitable to life, and eventually to humans. The theoretical process would involve releasing the vast quantities of carbon dioxide trapped in the polar ice caps and the soil. This would thicken the atmosphere, which would in turn warm the planet through the greenhouse effect, allowing liquid water to become stable on the surface. While the concept is a staple of science fiction and a source of intense debate among scientists and ethicists, the current scientific consensus is that terraforming Mars is not feasible with present-day technology, as there simply does not appear to be enough easily accessible carbon dioxide on the planet to create a significant and lasting greenhouse effect. Nevertheless, it remains a powerful and aspirational long-term goal, a testament to our species' enduring dream of transforming the Red Planet into a second home. And so, our journey across the rust-red plains and through the deep chasms of time comes to a close. We leave Mars as we found it, a world of profound silence, bathed in the faint light of a distant sun. It is a planet of ghosts, the ghost of a thicker atmosphere, the ghost of a global ocean, the ghost of a magnetic field that once shielded it from the cosmos. Every feature we have explored, from the towering peak of Olympus Mons to the deepest trenches of Valles Marineris, is a monument to a past that was far more dynamic and perhaps far more hospitable than the stark reality of the present. The story of Mars is written in the language of geology, a 4.5 billion year epic of planetary evolution, of life-giving potential, won and tragically lost. For now, our only presence there is robotic, a fleet of tireless surrogates that act as our eyes, our hands, and our chemical senses. They inch across ancient lake beds and listen for the faint tremors of a cooling world, piecing together this grand, complex history for us, one drilled rock and one panoramic image at a time. The ultimate questions, of course, remain unanswered. Was there ever life in those ancient waters? Could it, in some form, still persist in the hidden, briny aquifers beneath the ice? The answers are locked away in the Martian soil, waiting for a future mission, and perhaps a future generation, to unearth them. Mars remains the great object of our planetary imagination, no longer a home for fictional canal builders, but a tangible destination, a formidable challenge, and a crucial next step in the human story. It waits for us, a silent, frozen world, holding the secrets of our solar system's youth. And as we continue to gaze upon that red point of light in our own sky, we are no longer just looking at a neighboring world. We are looking at a destination, a history book, and a mirror reflecting the boundless reach of our own curiosity.